One of the concepts they really stress on the SOL are sound waves. They love sound waves. A sound wave is a compressional or a longitudinal wave. And the way to remember that is just think of a speaker or a tuning fork. A speaker moves back and forth just like the hand moving back and forth, compressing the slinky, sending the wave along the slinky. So these are called compressional waves or longitudinal waves because the compression moves along the slinky. With the sound wave, it compresses the air molecules out in front of it and sends the wave outward along the air molecules. Tuning fork does the same thing. You strike the tuning fork, it vibrates back and forth, and it compresses the air on both sides of it as it swings back and forth, sending a wave out, a compressional wave. You can increase the amplitude of a compressional wave. You make it louder. So if I wanted to make this louder, and of course with a speaker, you hook up an amplifier to it to make it louder. And so what that does is that increases the distance that compression happens. You make a much larger compression. The speaker really starts to move when you crank it up really loud. Perhaps you've seen that in someone's stereo system or in their car. If it gets really loud, that speaker really moves back and forth. And so loudness is associated with amplitude. The pitch that you hear determines how high or how low the sound sounds to you. Like how high, like a squeaky bird, or how low, like a tuba. So that would be the pitch, and that's determined by how quickly it vibrates or the frequency that it vibrates. So frequency determines your pitch. Now with all of these, all types of waves, including sound waves, the pitch can change depending on the medium that it passes through. For instance, you see your light waves up here. You got this straw, or this a pencil. It looks like a pencil sticking down in some water, and it looks like it's bent here, because what's happening is the light waves goes through and hits the pencil, and then bounces back towards your eye. Well, down here it's got to pass through water, where up here it doesn't. And the water down here, it slows down the light wave, where up here it doesn't have to deal with that. And whenever you change the speed, whenever it hits something of a different density, if it hits a different medium, whenever you change the speed, you bend the wave a little bit. You increase or decrease the frequency a little bit, and it bends the waves. So with this one, with light waves, we see it bending or refracting the light. Sound waves can do the same thing as it passes through different mediums, and it'll change the pitch a little bit. Helium balloons, for instance, you've all seen someone, they breathe into helium and they talk real funny. Well, that's because helium is less dense. It changes the pitch of the voice. It makes it go to a much higher scale. And so sound changes, and light as well. All waves change when they move through different medium. They will change. They will refract in the case of light waves. And just remember that light and sound are the complete opposites. Whereas light travels fastest through outer space. That's where we talk about the speed of light. Nothing goes faster than the speed of light. It travels fastest in outer space and slows down as it moves through the Earth's atmosphere, as it moves through a gas, and then it moves through liquids, and then it moves through a solid. It slows down, slows down, slows down. Sound is the complete opposite, where it moves fastest through a solid, and then slows down through a liquid, and then slows down through a gas. And then, of course, in outer space, it doesn't travel at all. There's no sound in outer space because for a compressional wave, you have to have something for it to vibrate against, air molecules. And there's no air molecules in outer space for it to vibrate against.